So I'm not going to waste too much time here. This is going to be the start and goal of the show, and it has two absolute values, which are completely useless. We just negate them because they're always going to be one side, and we're going to get to that. So here we have a double integral, the absolute value of another absolute value, xy minus 1 to the nth power dy dx. Now, the first thing we're going to look at is how we're going to get rid of these absolute values because we can't integrate an absolute value. The innermost absolute value has an inside of just xy. Now, look at the bounds. X and y are both between 0 and 1, meaning that they have to be positive. So we have x is going to be positive, y is also going to be positive. And positive times positive is always positive. So we just have an absolute value of some positive number, which makes no effect because the absolute values, they change negative signs to positives, but they don't do much to positive numbers. So this is just xy in the first bit here. So now we have just one absolute value left over. This one is going to be a bit more complex to take care of. So x and y are both less than or equal to 1. So x is going to be less than or equal to 1, and y is also going to be less than or equal to 1. But if you multiply a number by a different number that is less than or equal to 1, you're going to get a number that is less than or equal to that original number. So like you can do like 2 times 0.5, where 0.5 is less than 1, and you get 1, which is less than 2. So basically, this one is going to be less than x, but we already know that x has to be less than or equal to 1, meaning that this entire chunk is going to be less than or equal to 1. And if you're going to subtract 1 from that, you get a negative number. And taking the absolute value of a negative number gives you the positive version of that negative number. So basically what this absolute value does is it takes the negative of the inside because this is always negative. And here we have, so this would be negative xy plus 1. So we're going to write it as 1 minus xy because that looks better. To the nth power dy dx. Now, this is now a standard sort of multivariable integral. And I'll admit I'm not the best at these multivariable stuff, so if my process is a bit chunky, then well, perhaps then yeah, I can't do much better. So first thing we're going to do is substitution. We're going to let t be equal to this xy here. We have t equals to xy, and y, if we're going to isolate that, is equal to t over x. So we have dy is equal to dt over x. This 1 over x we can then drag out to over here. And so now we have a different integral from 0 to 1 still. 1 over x, and then a different integral. If we're going to plug in 0 for that, we still get 0, so this one is still 0. Then, if we're going to plug in 1 here, 1 for y, t equals to just x, so we have an upper bound of x here, and then 1 minus t to the nth power dt dx. Alright, so the next thing we're going to do with this, we're going to actually do another substitution. This time we're going to use s. S is equal to 1 minus t here. We have t equals to 1 minus s, and so dt is equal to negative ds. Now the reason we're going to do that is because we don't want this 1 minus t to the nth power, and doing the substitution gives us the bounds of integration. First of all, from if t is equal to 0, s is going to be 1 minus 0, which is going to be 1. If t equals to x, you plug in x for this, so we have 1 minus x. So there's a bound, and then we have just s here to the nth power, and then negative ds. This negative sign we can use to flip the bounds, and dx here. So flipping the bounds is good because now 1 is going to be the higher value, 1 minus x is going to be a lower value, because x is always positive. So we have here, I'm going to go from 0 to 1, 1 over x still, another integral from 1 minus x to 1 of this s to the n dx. Now that's just a standard integral, nothing too fancy to talk about there. So we have now integral 0, 1, 1 over x. The antiderivative is going to be 1 over n plus 1, so we're actually going to drag that out to the outside, 1 over n plus 1. And then rest is just s to the n plus 1 plugged in with these values. So first of all, it's going to be 1 to the n plus 1, which is going to be 1, minus, and then 1 minus x to the n plus 1 was still 1 minus x to the x plus 1, n plus 1, dx. Alright, so we got rid of one integral, and this bit, if you were to take it apart, I don't think it converges, but yeah, you can try that. You do limits or whatever. This instead, we're just going to do another substitution, and we're going to use a nice little harmonic sum. So u is equal to 1 minus x, and thus x is then going to be equal to 1 minus u, and dx equals to negative du. So that's the substitution. And so this 1 over n plus 1 stays out here still. And then we have an integral. Now, these bounds just sort of flip. So from 1 to 0 of 1 over x turns into 1 over 1 minus u. And then this next bit, 1 stays the same, minus this part is just going to be u, so u to the n plus 1 du. Negative du, but that negative du switches our bounds of integration to normal. Now this next bit is going to be a harmonic sum, so not a harmonic sum, this is going to be a geometric sum. So this one is going to be a sum from, I think it's 0 to n of u to the k. So I'm going to do that. This k looks a lot like an n, equals to 0 to n of u to the k du. This is going to be n. My k, n, and u look exactly the same, and that's just how it is. So next bit, we're going to switch this, and this is going to be just a basic integral, again, nothing to talk about, equals to n plus 1. 1 over, and then we have another sum. Our k equals to 0 to n. Okay. Doing this in our heads, we have integral from 0 to 1 of u to the k du, which is going to be u to the k plus 1 over k plus 1 evaluated from 0 to 1. So if you plug in 1 to that, you just get 1 over k plus 1. And then if you're going to take 0 to that, that just becomes 0, because 0 to any power is always going to be 0. And here, I don't think we're going to be using 0 to the 0. So here, instead, what we get is just 1 over k plus 1. There might be some debate based on, like, 0 to the 0 limit stuff, but I'm not going to talk about that. We're just going to assume this is what it is. And so next, we're going to shift the k values here. So you can think about it as like a number line, right? And then, so this is going to be 0, this is going to be n, and so k is from this range. And so the output value is going to be 1 over k plus 1. So what you can actually do is shift that to here, n plus 1, and 1. This is going to be our new k value, and instead, this part is just going to be 1 over k. Unrelated note, but I just wanted to draw a picture. So we have 1 over n plus 1. This bit is going to be some k equals to 1 to infinity, not infinity. K equals to 1 to n plus 1 of 1 over k. And so this is now in the form of the harmonic sum series, whatever. And so you can just substitute that in. When I'll put that in the numerator here, so it's going to be h harmonic n plus 1 over n plus 1. And this is the final solution. It holds for, I think, all n is a positive integer. About the negatives, I don't really know, but honestly, I don't think anyone's going to plug in negative numbers to this formula. And that's it. So, two absolute values, completely useless. A basic sort of multivariable integral, and the harmonic series to sum it off. I think that's a pretty cool one, honestly. Alright.